So welcome everyone. So now Tomek is going to give us the third lecture on the Amplitude and positive geometries. Please go ahead.
Thanks a lot, Stefano. Yes, I realized when I'm looking at this title that it says amplitude and positive geometries. I think it should be positive geometries and amplitude because the amplitude I will just touch in the last lecture only. So it's mostly about setting the stage for what the amplitude really is and how to think about it. And what we have done in the last lectures. So in the last lecture really. So in the first one, there was some motivation, but in the last lecture, I defined for you what a positive geometry is. So you remember that yes, positive geometries are these geometries with boundaries, and then there's a differential form which has very particular behavior at these boundaries. It's logarithmic, and then you can take residues and you can go to boundaries and have the differential form there, and then you can continue until you arrive to points, and at points which are zero-dimensional boundaries, you get a zero form, which is either plus or minus one. So that's the definition of the positive geometry. And I discussed polytopes. So a very particular case, if you take the ABHY kinematic associahedron, so that's a particular embedding of an associahedron. So it's a polytope with a structure, boundary structure of an associahedron. You can embed it using this ABHY construction, can embed it directly in the Mandelstam, so planar Mandelstam space. And what you can do, so it's a polytope, it's a convex polytope. You can define a logarithmic differential form, so canonical form on this object. So you can find this canonical form, which has these properties which I described. And then from this canonical form, what you can extract, you can extract the amplitude for biadjoint or adjoint partial. So it's a partial amplitude. So I put here partial in this biadjoint scalar theory. Okay, so that was the first example where the positive geometries were useful because there is a relation to physics. And if you didn't know anything about Feynman diagrams, you still are using this prescription. You can find all the three-level amplitudes in this biadjoint or in the adjoint scalar theory. Okay, so that was the goal which I set up at the very beginning in the first lecture, saying that we want to understand how to avoid using Feynman diagrams and just go directly to geometry and just extract the answer from geometry. Okay, but this was done. So this was purely this geometry was polyhedral, which means that it was just a convex polytope. But in order to study some more complicated theories, in this case it was a scalar theory, quite simple theory, quite easy to write Feynman diagrams, especially at 3 level. But if you want to go to something more complicated, like for example n=4 super n meals, then this positive geometries which will be associated to scattering amplitudes for n=4 will not be polyhedral anymore. There will be curvy versions, the curvy versions of polytopes. So probably you are not familiar with such objects, but these objects, they naturally live in a Grassmannian space. As a convex polytope lives in a projective space, so we discussed projective spaces in the last lectures. If you generalize this projective space to a Grassmannian, which I will define in a second, then you can also define bounded regions there, but these bounded regions will not look like polytopes anymore. They will look like a curvy versions of polytopes. So this is exactly what I want to discuss today. So for n=4 super n meals, and I just focus on planar limit of it in this series of lectures. So for n=4 super n meals scattering amplitudes, we need curvy, so curvy version of polytopes. So these are bounded regions, but they are not, so that the boundaries are not linear. They're not given by linear constraints, but they are given by some higher degree polynomial constraints. And this naturally leads to a notion of a Grassmannian. Let me just maybe do like this. So Grassmannian is a particular space, which I define in a second. But even more importantly, to the part of the Grassmannian which is called a positive Grassmannian. Okay, so as I said, the polytopes, they naturally live in projective space. The generalization of projective space is this Grassmannian. And in order to be able to discuss this more complicated gauge theories, the supersymmetric gauge theories like n equals to 4, we need to go to this curvy space. Okay, so in this lecture, I will still not define what the amplitude is. I will just prepare you. So I need to define what the Grassmannian is and what a positive Grassmannian is. And I will just give you some properties which will be relevant later for the amplitude, but I'll mostly focus on that. And one of the important things which one important statement about positive Grassmannian is, I will define in a second, that positive Grassmannian is a positive geometry. That's one statement. And because it's a positive geometry, it's usually when we talk about positive geometries, if you look at the definition, that there are some important ingredients in these definitions. For example, boundary structure is an important ingredient. So one of the important questions to ask is, what is the boundary structure of this positive Grassmannian? And this was answered. So I just give you two references for the Grassmannian and the positive Grassmannian. So one was done by Postnikov quite a long time ago. So this boundary structure of the positive Grassmannian was studied in this paper, and then in 5605, that's paper by Nima and collaborators, which describes how this positive Grassmannian fits into this story of scattering amplitudes. It's not yet amplitude, it's 1 year before amplitude was born, but it describes all these properties of positive Grassmannians which are relevant for amplitudes and later for the amplitude. Okay, so the plan for today is I just want to describe what the Grassmannian is. I want to tell you what the positive Grassmannian is, and I want to I just give you one example how to think about positive geometries associated to Grassmannians. Okay, so there is a procedure which allows you to define new geometries from the positive Grassmannian. Okay, so that's the goal for today. So what is a Grassmannian? So Grassmannian is a space which we call G, K, N. So it depends on two parameters, K and N. So it's the space of all K planes in an n-dimensional space. Okay, so we take an n-dimensional space and on all K planes. So if you take one planes in n-dimensional space, so you take a collection of lines, that defines for you what a projective space is. So Grassmannian is a natural generalization of that. Instead of one planes, if you take K planes, then you get a Grassmannian. Okay, and the important thing is that, we are talking now about K planes in n dimensions. So now we would like to describe these K planes. So in order to describe the K planes, what we'll do, we'll just specify them by a matrix. So if you have a K plane, so if you have a one plane, you can just define a vector, which is a vector which just defines for you this. So one plane is a line, so it defines for you a line. In order to define a K plane, you need K such vectors. So in order to define what the element of Grassmannian is, to specialize and to find some parameterization of this K plane in n dimensions, what you need to specify K n-dimensional vectors. Okay, so to specify a point in a Grassmannian, we give K n vectors. Okay, so that are just K n vectors, and then this, if I take all possible linear combination of this K n vectors, then you'll get a K plane. Okay, so how can I think about K vectors, K n vectors? I can just arrange them into a matrix. So there'll be the first K vector C11, so n coordinates, and then I can take a second one, 2n, and so on. I take K of them, and I can arrange them in a matrix. So this is a k times n matrix, and if I have k n vectors, then I can always define such a matrix. I need to be a bit careful here because we are not talking about a collection of k n vectors. I defined the Grassmannian as a space of all k planes, but it can happen that there are different vectors defining exactly the same k plane. So in order to remove this redundancy, so this redundancy corresponds to just change of basis of this k plane. In order to remove it, so differently, I can go from one of the bases to another basis by just performing a GLK transformation on this matrix. So if I rotate it, just multiplying from left by GLK transformation, k by k matrix, I will get a different set of k n vectors, which defines exactly the same plane. So in order to talk about Grassmannians, I have to just I have to remove this redundancy here. So I need to make sure that there's one matrix corresponding to one point inside of the Grassmannian. So what I need to do, so let me just write it. So since any non-degenerate linear transformation of these k vectors. So by linear transformation, I mean change of basis, really, of this k plane, gives the same point in the Grassmannian. I need to remove this redundancy. So I need to just remove this GLK redundancy. Okay, so how do I do that? I mean, there's a simple way to do that. For example, what you can do, you can just take your matrix and just fix some of the entries of this matrix such that you get a unique collection of vectors defining every possible k plane. So, for example, what I can do in order to remove this GLK redundancy, I just take C to be, for example, in the form the identity matrix here. So this is a k by k identity. And then there will be some remaining coordinates here. So ck plus 1, C1 k plus 1 up to C1 n up to ck k plus 1 ckn. Okay, so if I fix this first part of this matrix, then every such matrix corresponds to a single point in a Grassmannian. Okay, this also tells me that I can calculate what's the dimension of the Grassmannian space. Okay, so there is a question. Sorry. Yeah.
There is a question in the chat.
Yes. So the question is, what do you mean a point in a Grassmannian? You mean which specific k plane in the space of k planes? So what I mean here, so in this case, when I already fixed my redundancy, I mean the k plane. So yeah, I have one n vector here. So there's one vector pointing somewhere. There's another vector here pointing somewhere else, right? And I have k such vectors, and I take all linear combinations of these k vectors. So if I take all linear combinations, then I get a k plane there. It's the same way as if I have one vector, I take all possible linear combinations. So it's almost I multiply by any real number, I get all points on the line with the direction of the line specified by this vector. So the generalization of it is just you take k vectors instead of one vector, and then you take all possible positive combinations of it. These are not positive, all possible combinations of it. Yeah, it's a specific k plane. Yes, every point in the Grassmannian is a specific k plane, and the Grassmannian is a collection of all possible k planes in n dimensions. Yes. Okay. So now, because of that, so I can just looking at this formula at this parameterization here, I can immediately say what the dimension of the Grassmannian is. So I said that for every matrix like that, I get a single point. So I just need to find how many independent variables I have here. So I have, if I just look at this matrix here, there's k times n minus k c's Okay, so the dimension of the Grassmannian k comma n is just k times n minus k. Okay, so that's one important thing. So you can immediately see, so let's see some particular examples. So if k is equal to 1, then g1 comma n is the same as the projective space n minus 1. So it's an n minus 1 dimensional space. So you can see that if I plug in k equal to 1 here, I get 1 times n minus 1, that's n minus 1 dimensions. And this is exactly the dimension of this projective space of, n minus 1 dimensional projective space. So the Grassmannian for k equal to 1 just reduces to this, this object which we already know. So those are all points in R to the n modulo non-zero rescalings. But when you go to k equal to 2 and higher, then you can immediately see that this object becomes quite high dimensional. Okay, another question: do the planes need to contain the origin? Yes. So very good. Thank you. These are linear spaces. Yes. So they're not affine. They're linear spaces. All of them go through 0. Yes. So the picture for example, P1. So P1, which is the same as G1 comma 2, would be all lines coming through the origin, all of them. Okay, so this is collection. So this is a single point. This line is a single point in G1 comma 2. Okay, and all of them have to go through origin. I mean, that's, okay. Okay, so this is what the Grassmannian is. What I was saying that if you look at this dimensionality here, then you immediately see that this can be very fast, very high. Because, for example, if you take the simplest case, which is not a projective space, so the simplest case is when k is equal to 2 and n is equal to 4. In that case, the dimension of G2 comma 4 is 4. That's already something which is difficult to visualize. Okay, so we need to abandon this idea of so not abandon, maybe, but it's difficult to visualize the geometry inside of Grassmannians because they are quite high dimensional. Okay, and they on top of that there will be also curvy. So it's quite often it's very difficult to get some intuition about what these objects are. So in many cases, instead of thinking about geometry and trying to build some geometric intuition, we usually think about some combinatorics and try to build the intuition from combinatorics or from some algebraic description of this object. Okay, so that's what the Grassmannian is, and the next step is I want to define what a positive Grassmannian is. So in the name of positive geometries, there's positive, and we already saw it when we defined this ABHY as a sechedron. We saw that it was defined as some intersection of a positive region with some affine subspace, and this positivity in this context is always somewhere there. And in the case of the Grassmannian, one can define a positive part of the Grassmannian, and that's an interesting object. So let me just define that. So to be more precise, I should again define a totally non-negative Grassmannian, but I will always refer to it again as positive. That's kind of conventional in this business here. Okay, so I defined a totally non-negative or positive Grassmannian G plus, so I indicate by plus the positive part of it, k comma n. Okay, there's a question?
Yeah, so you said that G2 comma 4 is the first non-trivial example?
Yes.
But what about G2 comma 3? Like that has dimension 2, right?
That's correct. Thank you. Yes. So k equal to 2, n equal to 3, G2 comma 3. There is, if you think about what G2 comma 3 is a collection of two-dimensional subspaces inside of three-dimensional space. Okay, but every two-dimensional subspace in terms of inside of three-dimensional space can be equivalent. I mean, can be described by the basis of this two plane, or it can be described by the orthogonal vector for this plane. Okay, so there is something which is called a duality. So Grassmannian duality, which tells you that in more general, g k comma n is the same as g n minus k comma n. Okay, so you're right that it looks like g2 comma 3 will be a non-trivial example, but it's exactly the same as g1 comma 3, so it's still projective space. Okay, but it's a very good question. Yes. Okay, so the positive Grassmannian. So these are all matrices. So this is a subset of the Grassmannian. So that's a space of all positive, positive k by n matrices of the maximal rank. So of the rank k, modulo this GLK. So modulo GLK. Okay, so I need to tell you what the positive matrix is. So it's a k times n matrices of rank k modulo GLK. That's what the Grassmannian is. And in order to restrict the positive part, we just need to restrict to positive matrices. So positive matrices are matrices with all ordered minors positive. So what is an ordered minor? I take just some columns of this matrix. So this is a matrix which is k by n matrix. So there's a k rows and then columns. I take some I1, I2 up to ik columns of this matrix. Now I have a square matrix, so k times k matrix. I can take a determinant, and this is what I call the maximal minor. And the idea is that positive matrix is a matrix where all these maximal minors are positive. Okay, so that's not every element of the Grassmannian will be an element of the positive Grassmannian, but every element of the positive Grassmannian is an element of the Grassmannian. So just to say,
how do you choose the sign for I1, I2 up to ik? There's like a -1 to something, right?
So what I mean, so you mean in the definition of the determinant?
Yes.
Yes, but what I mean by maximal minor, I mean really taking exactly the columns which I have and calculate the determinant in the way you usually calculate determinant. So when you calculate determinant, there'll be some minus signs. But the point is that after I calculate this determinant, it has to be positive. Okay, so let me maybe just let me just give you an example. So if I take g plus 2,4, that's the simplest possible example. So this should be matrices which will look like 1, 1, 0, 0. So gauge fixed. So sorry, I'm using word gauge fixed because that's what usually people use. GL2 fixed, so it's fixed with GL2, and then there's C13, C14, C23, C24. Okay, so this is an element of the Grassmannian, but now I want to restrict to a positive part of it. So not all C's are allowed now. So what I need to do, I need to find all maximal minors of this matrix. So then what are maximal minors? I will label them by their columns. So if I take a column 1, 2, then I have just a minor of the column 1, 2, that's 1. I can take 1, 3, so that's 1, 0, C13, C23, that's C23. And I can continue like that. Okay, so 1, 4 is C24, 2, 3 is minus C13, 2, 4 is minus C14, and then 3, 4 is C13, C24, minus C14, C23. Okay, so these are the maximal minors. Okay, there are some minus signs here. There are also some minus signs here. But now what I demand to restrict to an element of the positive Grassmannian, I just demand that all of these things are, let's say, non-negative. Okay, this gives me some constraints. So it just tells me that I cannot take any C's. For example, I need to take a positive C23 and a positive C24, but a negative C13 and negative C14, and additionally, this condition has to be satisfied. Okay, so if I find an element, if I find C's which satisfy all these 6 inequalities, then I found an element of the positive Grassmannian. So there's a question: what is the intuition of this definition? It's a good question. Mathematicians like to define positive parts of things, and I'm not sure if I can offer some easy explanation. So for the positive part of the projective space, so G plus, for example, 1,3. So it turns out, so the projective space 1,3 is just it's almost identical to a two-dimensional real space. So this is almost like R squared. But I'm sorry, I wanted to say G1,3. G1,3 is a projective space, so it's almost like R squared. But G plus 1,3 is like a simplex, so like a triangle. It's like a triangle. Okay, so so it's a simplex in two-dimensional space. So the generalization beyond the projective spaces, beyond k equal to 1, you can think about this as generalizations of simplices inside of your space. Okay, so it's G plus 2,4 is like a generalization of the simplex into the Grassmannian space. Okay, so that's the closest I can give you to an intuition. Sorry, I see some more questions. Did I miss one? Positive still non-negative for G plus. Yeah, so when I say, so one should really be careful here. I'm always not very careful, but the totally non-negative means that yeah, sorry, let me just remove this part here. I should say non-negative here or positive. Okay, so you can define a non-negative part. In that case, everything, so all the inequalities are soft inequalities, or you can define a positive part, which is like an inside, like really an open subset of it, where everything is a positive. So all the inequalities are sharp. Okay, so in the sense that you can define two different objects, but we usually do not distinguish between them and always refer to it as positive and always think about these inequalities. Okay, and then there's one more question. Is it obvious that these inequalities can always be satisfied consistently for any k, n? So the point is that for any k and n, there exists at least one point which satisfies them. Okay, so in the sense that so your question, if I translate it, your question asks, is G plus k, n non-empty? And the answer is yes. There are always at least one point, and there's many points. There's infinitely many points. But I mean, you can take some examples. So let's say here we could find some solution where so let's say 1, 0, 0, 1, 1, minus 1, 2. If I'm not mistaken, this is an element of the G plus k 2,4, which means that it's not empty. So it always can be solved, and some C's can be found which satisfy all these conditions. And this is true for any k and n. So one can easily show that the positive Grassmannian k, n is non-empty. Okay. Good. Okay, so what the positive Grassmannian is some bounded region inside of G, k, n, and it has a very well-defined boundary structure. Sorry, you probably mean 2, 1. Thank you. I think that you're correct. I'm just not used to, yeah. It's not so easy to guess, but yeah, it's always possible to construct. But thank you. Yes, you're right. Okay, so positive Grassmannian is a bounded region inside of G, k, n, and it has a very well understood boundary structure, which was studied by Postnikov, and there's a beautiful story, and it's an important story because it later on, when one talks about amplituhedron, amplituhedron will be just an image, sorry, the image of the positive Grassmannian through some linear map. And the boundaries of the positive Grassmannian will correspond to physical boundaries of the amplituhedrons, the boundaries which correspond to singularities of amplitudes. So knowing boundary structure of positive Grassmannian is an important thing. And one of the exercises for today, which I should publish and I haven't yet, so I'll publish after the lecture, is to find a boundary structure of G plus 2,4, which is already a difficult task. It is important to know this boundary structure in order to be able to talk about the positive geometry, because we always want to talk about boundaries and how the differential forms behave at these boundaries. The question is all C equal to 0 a valid solution? Yes, it is, and it's very good point. So you can see that if I put all C's equal to 0, then all these inequalities are satisfied. Yes, but if I took a sharp inequalities here, so if I talk about inside, so the open part of the positive Grassmannian, all zeros will not be there. So this point 1, 1, 0, 0, 0, 0, 0. It is inside of. Let me use some slightly different notation. So it is inside of the non-negative Grassmannian G 2,4, but it's not inside of the truly positive part, right? Because these inequalities would turn from soft to sharp, and zeros do not satisfy that. So this point is on the boundary of the positive part. Okay, that is a good point, good question. Okay, so now what I wanted to do, I just wanted to give you some idea how this boundary can look like, and just starting from very simple, some very simple examples. So let's take a look at first projective spaces, G plus 1, 3. Okay, so what is G plus 1, 3? It is a set of all matrices which can be written like this. I already fixed the first entry to be 1, so I explicitly written it in some particular patch of this positive Grassmannian, of the Grassmannian, and I have two variables C2 and C3, so it's a two-dimensional space. And now I can find what the maximal minors are. So maximal minors in that case is just 1. You just take the first column and the determinant of it. And then C2 is a maximal minor, and then C3 is a maximal minor. So all of them have to be non-negative. So that's the space. So the space is all matrices with this entry C2 and C3 positive, non-negative. Okay. So now what we'd like to do, we'd like to study what the boundary structure of this object is. So later on, we would like to write, so I claim that positive Grassmannian is a positive geometry, which means that we would like to write a canonical form on it. And in order to check that this is a canonical form, you need to know boundary structure, because you need to know where to check your conditions for the positive geometries. Okay, so we want to find what the boundary structure is. And in this case, there are two obvious boundaries. Right, so there are points which are, I mean, if I take C2 equal to 0 and C3 equal to 0, sorry, C2 equal to 0 or C3 equal to 0, then I go to the boundary of this object, because for C2 positive, I'm inside, and these are points inside of the G plus 1, 3. But when C2 is negative, I'm outside, it's not an element. So C2 equal to 0 is a boundary of this object. Okay, so there are some obvious boundaries. So the obvious ones. So if I take C2 equal to 0, that's an obvious boundary. Or if I take C3 equal to 0, it's an obvious boundary as well. And I give them names. So I call this boundary B2. So if I take C2 equal to 0, all matrices which I had, I don't have generic matrices. I reduced my class of matrices to these matrices only. Okay. So this boundary consists of all matrices of the form 1, 0, C3 when C3 is non-negative. And similarly, this is I call B3. So this is a set of all matrices of the form C1, C2, 0, such that C2 is non-negative. Okay. So these are two obvious boundaries of this object. But it turns out that there's a third boundary which we cannot see. So because we chose this parameterization of our matrix, we cannot see it explicitly in this patch of the Grassmannian. But there's another boundary, which is when C2 goes to infinity and C3 goes to infinity in a very particular way. So it turns out that there's a third boundary as well. So there is a non-obvious one. And so this non-obvious, in order to find it, what we need to do, we need to remember that if I have a point which is parameterized, so this is an element of G1, 3. This point represents a plane. So I should really think about an equivalence class of points. So this point is equivalent to a point which looks like this. If I take this point and multiply by a common constant, let me take C1 positive here, then this defines the same point. So this is the same point in G1, 3. Okay. It's the same point because it defines exactly the same one plane. One plane in that case is a line, but it doesn't matter if I take this vector and all its multiplicities, or I take this vector and all its linear combinations, so all their scalings. This is exactly the same point in the Grassmann. So now if I look at this point here, then I can see that there is some limit where I can approach, when I can get to one more boundary of G plus 1, 3. Okay, so what we do, we take the limit when C1 goes to 0, C2 goes to infinity, and C3 goes to infinity, but so such that C1 times C2 goes to some constant, let me call it D1, and C1 times C3 goes to another constant, which I call D2. Okay, so what happens is that when I take this limit, then this point, so this C1, C1, C2, and C1, C3, it goes to a point which looks like 0, D1, D2. And then again, because this is an element of the Grassmannian, I can always rescale it. So I can remove one of these parameters. So I can rescale it, and let me use a different letter. I can bring it to this particular form. Okay. So there's one more boundary, and if you look at the definition, so here, if you think about the Grassmannian, the Grassmannian has a cyclic structure, and you shouldn't distinguish between C1, C2, and C3. We just chose some particular patch. We broke this symmetry, the cyclic symmetry of this object, and because of that, we cannot access all possible boundaries. But if you look at these two boundaries, it's natural that there should be a third one as well, right? I mean, here the 0 is at the second position, here the 0 is at the third position, but because the Grassmannian is a cyclic object, there should be also a boundary where the 0 is at the first position. It's just we cannot access it using this particular patch of the Grassmannian. Okay, so but we can find it if you take the C's in this particular patch to infinity. So that's the third boundary. So let me call B3 is a set of all matrices, which looks like 0, 1, E1, such that E1 is non-negative. Okay. So that's what the object is. So we can start to depict it. So we have in a bulk, so it's G plus 1, 3. It has 3 boundaries. So one is B1, B2, and B3. And then you can, for example, take either of them. So let's take B1 again. So B1 is equal to, sorry, let me check, 1, 0, C3, such that C3 is non-negative. This set of matrices again has 2 boundaries. So I mean, you cannot see it immediately, but there's an obvious one where C3 goes to 0, right? And so there's this point here. Or not. I'm sorry, I'm just looking at my picture. I'm sorry, I just did the other way around on my picture. 3 and 2. Okay, so if I take B1, and take C3 equal to 0, I get matrix which looks like I'm sorry, I'm just confused now. I'm sorry. Because I called this B1, I should call it B1. Okay, so this is B1. So B1 is really this matrix. I'm sorry about that. Okay, so if I take that C3 equal to 0, I'll get a single point. Okay, so this is at this point here, 0, 1, 0. So there is a single point here. And then similarly, if I rescale everything, I can go to a boundary where this 1 will turn into 0. So if I take C3 to infinity, I approach another boundary, which will be here. So this point here is just 0, 0, 1. And then this point here is 1, 0. Okay, so if I study all the boundary structure of this object, you'll realize that G plus 1, 3 is just, so G plus 1, 3 is just a triangle in disguise, really. Okay, so the boundary structure of this object is exactly the same as the boundary structure of the triangle. And this can be generalized later, as I will come in a second. And then you can define also the canonical form. So the canonical form on G plus 1, 3 is very easy to write using this parameterization. So if I go back, if I go back here, I parameterize my Grassmannian, positive Grassmannian, using two parameters C2 and C3. And it turns out that in this parameterization, the differential form of the Grassmannian is just d log of C2 wedge d log of C3. So in other words, dC2 over C2 wedge dC3 over C3. So if you just look at this differential form, you will notice that it has two obvious boundaries, two obvious singularities when C2 and C3 is equal to 0. So there are the two boundaries which we discussed, the obvious ones. But this differential form, it also has a non-trivial singularity when C2 and C3 goes to infinity. Okay, and in order to expose that, what you would need to do, you would need to change variables and change variables. I don't want to make a mistake now, something like 1 over C2 and C3 going to 1 over C3, and you would notice that there is a third boundary there as well. Okay, the third singularity of this differential form. Okay, so that's an important statement. We have a positive Grassmannian, in that case, it's a positive part of the projective space, and this is a positive geometry which has a canonical form, which is given in this particular. I mean, this is the canonical form for this in this particular parameterization. Okay, and similar calculation can be done. So similarly, G plus 1, n is a simple. I mean, it has a boundary structure of a simplex in n minus 1 dimensions. And then when you go beyond k equal to 1, things start to be complicated. So if you take, for example, G plus 2, 4, that's, I mean, the one way of parameterizing it would be, these are all the matrices which look like this, such that alpha, beta, gamma, and delta are positive, non-negative. You can check, it's slightly different parameterization, but you can check that in this parameterization, it's a four-dimensional object with all the maximal minors non-negative. If alpha, beta, gamma, and delta is non-negative, you can check it immediately, just calculating them all the maximal minors. Okay, so now, so this object is four-dimensional, so it's a bit more difficult to visualize. So the boundary structure is not so easy to draw because you would need to draw a four-dimensional object. But it is even more complicated. So the boundary structure is not the boundary structure of any polytope. It's much less intuitive than that. So the boundary structure is not easy. And I give you this as an exercise. So in order to find it, you need to do a similar thing, which I was doing for the G plus 1, 3. There will be some obvious boundaries in these parameterizations, but there will be some boundaries which are not obvious in these parameterizations, and one needs to take another parameterization in order to expose all of them. So if you look at the problem sheet, I indicated how many different boundaries you should find, but the task for you is to try to find all of them and try to find all the matrices which parameterize all the boundaries the three-dimensional ones, two-dimensional ones, one-dimensional ones, and zero-dimensional ones. Okay, good. Okay, so this is a positive Grassmannian. So I maybe pause here for a second and ask if there are any questions, or is it quite clear what a positive Grassmannian is? So the definition is all K by N matrices with positive maximal minors, and the new object probably for you. So I mean, in order to be able to talk about it, you probably need to play with it and to get some intuition. How does it look like? Okay, are there any questions about the positive Grassmannian?
I have a question about the differential forms.
Mm-hmm.
So it seemed like the differential form from last lecture was parameterization independent. It was written in such a way that you didn't have to really choose coordinates, and so I was wondering if it's possible to do something similar for the positive Grassmannian. And I guess I also have a question maybe for last time, which was how would you derive or find such a differential form that is coordinate free, or I guess maybe even in the non-coordinate free case. How do you determine these differential forms?
I'm not sure what you mean by coordinate free. I mean,
so you'd written it in terms of like bracket, y, z1, z2. There was, you didn't actually choose like here a c2, c3. Yeah. So by coordinates I mean a parameterization where you're choosing like a 1, 0, 0, 1, alpha, gamma, beta, delta, whatever.
Yeah. So you need to think about the positive Grassmannian as a very particular. So let's say, for example, this one, G plus 1, 3. It's not every possible simplex. It's a simplex with vertices. So one of the vertices is at 0, 0, and the other vertices are pushed to infinity. So it's just a positive quadrant, really. Okay, so positive quadrant is a simplex somehow. So positive Grassmannian is just so it's not a generalization of any possible polytope. There are no vertices. So the position of vertices is fixed for you from the start somehow. Okay, that's the reason why it doesn't have any information about some external data as our polytopes had. So the polytopes were specified by their vertices, right? And then there was, so if you remember from last time, there were z's. So there are positions of vertices, okay, and then there was this y also, which looked like 1, x, and y, and maybe more coordinates like this, okay. And the differential form depends on both of them, okay. So now the meaning of the c's here, or this alpha, beta, gamma, delta, is it is replacing this x's and y's. So the z's are somehow in a fixed position. That it's not part of the data. So if you remember, yeah, I'm not sure how to answer this question.
Okay, is it possible to write it in a form like with brackets?
No, because there are no brackets of. I'm sorry. I said sorry. It is possible with brackets. Yes. I'm sorry. Let me just do that. So in this case, for example, so G plus 2, 4, the form will look like D K times N C modulo GLK divided by 1, 2, 2, 3. Sorry, I have just 4 of them. So this is 2 times 4. 1, 2, 2, 3, 3, 4, 4, 1. Okay, so that will be a form in terms of brackets. But these brackets now are brackets of this matrix here. Okay, so the only information that the only objects this differential form depends on is this matrix. There are no z's somehow.
Right, thanks.
Okay. Anyway, okay.
I
So
have probably a related problem. And is the differential form unique?
yes.
Okay, so I mean, how can I see that no matter how I change the coordinate, the differential form will always give me the same result? Is there an explanation?
So what do you need to do? You need to pick some parameterization. So you describe your positive Grassmannian in some very particular way. And in this particular parameterization, like for example, this one, you will find some differential form. In this case, the differential form will look like something d log alpha, d log beta, d log gamma, wedge d log delta. Okay, and then it is unique in the sense that, so first of all, it's the canonical form, so you can check that if you go to all the boundaries of G plus 2,4, you will find residues, and then at the end, when you arrive to the points, you get plus or minus 1. It means that it's a canonical form. Now you could reparameterize your Grassmannian and use different parameterization, not this one. What it would do, I mean, you would still get the same differential form, just written in different coordinates. Okay, so it's still the same form, just in different coordinates. And I mean, the claim is that it's unique. I don't know the proof for that, but it's always the same differential form, just written in different coordinates. It's the same for polytopes. I mean, you could parameterize them slightly different way, and but the differential form which you had at the beginning, after the change of variables, will be the resulting differential form.
Okay. Yeah, I mean, this is very natural to think the form is unique, but I cannot see why, if I choose a different coordinate and those d logs will always be the same.
So
I mean, I know they describe the same object, but it's weird to think that after transformation they'll still give the same answer.
I mean, it has to be every transformation which preserves the boundaries of the G plus 2,4, right? So it's like a reparameterization of it. And I don't know a very simple proof that that's the case.
Okay, I see.
In whichever parameterization you write it, you'll find exactly the same set of boundaries and exactly the same set of singularities of your differential form. And that shows you that this form is the same form, just written in different coordinates.
If I can,
Sorry,
you can add something like practical, like if you want to see if two forms are in different coordinates are the same form, you should write it as Tomasz has written up there when they were asking about like something that is not written in terms of coordinates. So you should write the form in terms of the minor of the matrix. And when you have write it in as a function of the minors, then you don't have your coordinate in the game anymore, and you can see if two forms are the same form. Like if you want to compare two
easy check. Okay.
Yeah, you're right. Yes, So yeah, you're probably right. Yeah, I should have said that this form always works. Yeah. So whichever parameterization you take and plug it into this form, in this case, for example, you can find that the minor 1, 2 is just beta, the minor 2, 3 is alpha, the minor 3, 4 is just gamma, and then 1, 4 is delta. So if you plug it here, you will notice that it's exactly this form.
Oh, yeah.
You can reduce it to this form. Yeah, thanks, Gabriel. Okay, I think that's yeah.
Can I ask you? Sorry, my internet got disconnected, so I don't know if you covered this, but do you have the same recursive structure here? Like, so when you go to the boundary, do you also have a positive Grassmannian intrinsically on the boundary? Is the boundary also like a positive Grassmannian?
Not all boundaries. So you need to notice. So notice the following thing. So let's start with G plus 2,5. Say, okay, this is a 6-dimensional object. Okay, when you go to a boundary of this object, the boundary is a 5-dimensional object, right? So the boundary is 5D. But this boundary is not a a positive Grassmannian. I mean, there's no Grassmannian with, so there is a projective space.
It's prime.
Yeah, but anyway, but if you go,
it's prime.
Because it's five-dimensional, right? So, but if you go further, if you take one more boundary, some of them will look like G plus 2,4, because that's a four-dimensional object. Okay, so what happens is that you have this full object, and then it's six-dimensional, and five-dimensional boundaries, they're not positive Grassmannians, they're just some parts of positive Grassmannians. But then if you go one step further to codimensional two boundaries, some of these boundaries will look like G plus 2,4. Okay, but there's a lot of boundaries which are completely different, and they are just parts of positive Grassmannians.
I see. Okay. So a related question to some of the on the uniqueness of the canonical form. So in the case of polytopes, because you have this recursive property, and that finally at the zero-dimensional boundary, you need residue 1. That fixes the uniqueness. I mean, even if you do any coordinate transformation to ensure that it is plus minus 1 at the zero-dimensional boundary, perhaps that fixes the uniqueness of the differential form. Like if one were to take like z going to any f of z, such that f of 0 is 0, that is the definition of the boundary that you gave.
Yes. So here's the same. So here's the same. So what can happen is that so here, so for example, in this case, the boundaries are also when alpha, for example, alpha goes to 0 is one of the boundaries of this object, right? And the differential form in this at this boundary behaves like this. So there's a d alpha over alpha. So there's a logarithmic divergence there. And when you take the residue at the boundary, you will get this 3 form as the answer. Okay, and then you can continue. So the structure of removing the d logs and just going to boundaries and still having a positive geometry, it is still here for the positive Grassmannian. It's just that these boundaries, they do not look like positive Grassmannians anymore.
I see.
Okay. So yeah, so for polytopes it's easy because every boundary of a polytope is a polytope. Here it's not so trivial. Okay, but still the same thing holds true, that if you go to the boundary, you get a logarithmic divergence. You just remove it, and then the remaining form just gives you the logarithmic form on the boundary. Okay.
Yeah. Thanks.
Okay, so why we are interested in positive Grassmannians? Because positive Grassmannians allow us to define new positive geometries. And one of these positive geometries is the amplituhedron, the other one is the momentum amplituhedron. But I want to, in order to show how new geometries can be derived from positive Grassmannians, I'll just give you one geometry, which is a polytopal geometry, which comes from the positive Grassmannian. So that might be quite counterintuitive. We take a difficult object like positive Grassmannian, and we will define a polyhedral positive geometry from it. Okay, and this positive geometry, which I want to define, is the hypersimplex. So positive geometries from positive Grassmannian. So I just wanted to tell you how it can be done in a simple setting where we can still visualize something, and then later on, using quite similar construction, we can define what the positive Grassmannian, sorry, what the amplituhedron is and what the momentum amplituhedron is. So let me just define for you what the hypersimplex is. So hypersimplex has also two indices, so k and n. So it's delta k comma n. It's the image of g plus k comma n through the following map, which is called the algebraic moment map. Okay, so the map is, I call it mu. It goes from g plus k comma n into r to the n. So that would be, so our polytope will live in the flat space, really. Such that if I take any element, so this is an element, so C is just an element of G k comma n, G plus k comma n. If I take this element, then what I need to do, so there's a formula for that. So I need to sum Pi, I'll explain in a second what I mean by these objects, I divided by the sum pi over c. Okay, so here I is just so this is just all possible k element subsets of the set n, which is just the set of from 1 up to n. Okay, so these are all possible subsets of with k elements where the entries, so the elements of this subsets are taken from numbers from 1 to n. Then this p here, these are just the maximal minors. So this PIC is the maximal minor of C, where this I here. So you remember when I talk about C, and if I take I1, I2 up to IK. If I take k columns, I can construct my maximal minor. So this I here just labels these columns. Okay, so I take all possible k element subsets of set of with n elements, and this k element subsets they just give me all possible maximal minors. Okay, so these are the maximal minors, and this E here, this E are just vectors which look like this: 0, 1 at position I1, 0, and then 1 at position I2, and 0, and so on. So there are ones only at positions I1, I2 up to IK, 0, 1, 0, IK. Okay, so that's what the definition is. So the hypersymbol is just image of. I take all possible matrices which belong to the positive Grassmannian k, n, and I just apply this map and I see which points I arrived at. And the answer is that the image of this object is a polytope, and this is a polytope which is called a hypersimplex. So I just give you a very, very simple example, and probably I need to finish after that. Okay, so the simple example is delta 1, 3. So by definition, this is just the image of the positive Grassmannian 1, 3. Okay. So if I take elements of G plus 1, 3, they look like this. So that they're matrices 1, C2, C3. And then I can calculate all these maximal minors. So now K is equal to 1, which means that I need to take a one element subset of the set 1, 2, and 3. Okay, so that are just 3 capital I's. So I is inside of 3, 1. So there's one of them, it's P1. So that's just the minor of the, that's just a 1 by 1 minor, so maximal minor of the, where I just use the first column. So in that case, just simply 1. P2C is just a minor using the second column, so that's just C2. And then P3, C is just C3. Okay, so these are my P's. And then what E1 is, so E1 is just 1, 0, 0. So there's just 1 at position 1 and zeros everywhere else. E2 is just 0, 1, 0. And then E3 is 0, 0, 1. So now I can just take this matrix and use all this information about P's and E's and just plug to the formula. So I have a formula here, and what you'll find that the mu of C is just a vector in R3, which looks like this: C2 over 1 plus C2 plus C3, and C3 over 1 plus C2 plus C3. So this is an element of R3, and let me call this element as, so let me parameterize my R3 using X1, X2, and X3. Okay, so this is my coordinate system. So every element of the positive Grassmannian G plus 1, 3 is mapped to one of these points inside of the inside of the R3. Okay, now notice the following thing. So notice that if I take x1 plus x2 plus x3, that's 1 over 1 plus c2 plus c3 plus c2 over 1 plus c2 plus c3 plus c3 over 1 plus c2 plus c3. So this is equal to 1. So the sum of all x's is constant, and in that case is equal to 1. More generally, it will be equal to k. Okay. So now, so the image is in 3 dimensions, but it lives at the hyperplane defined by this x1 plus x2 plus x3 equal to 1. So it's really a 2-dimensional object, and it should be a 2-dimensional object because it's the image of 2-dimensional object. Okay. So if you now just depict it, so you can just choose x1 and x2 as your coordinate system, because x3 it depends on x1 and x2, so we don't have to depict it. So x1 and x2. Then you will notice that all these points here, they always satisfy that x1 is positive, sorry, non-negative. x2 is non-negative. Okay, so if I take C2 and C3 positive, so C2 and C3 non-negative, then that's always the case, that x1 is non-negative and x2 is non-negative. And then additionally, x1 plus x2 minus 1 is x1 plus x2 minus 1 is also positive, so non-negative, sorry. So this just looking at this image here. So the image really what it is a triangle with vertices at 1, 0, and 1. Okay, where this is boundary x2 equal to 0, this is the boundary x1 equal to 0, and this is the boundary x1 plus x2 minus 1 equal to 0. Not sure if I got the sign properly here. Sorry, it should be minus 1. So negative. Okay, so you can see that. So what happens is that you started with a positive Grassmannian here, and then you use this moment map. You got the image, and the image is just a triangle. So just to say that the delta 1,3 is a triangle, this very particular triangle here. Okay, and then what you can do, so in all the cases where you define a positive geometry as an image of positive Grassmannian, as it will be, for example, for the amplituhedron, it is possible to find the differential form of the image just using the differential forms on the positive Grassmannian itself. So you remember that in the positive Grassmannian we had d log C2 wedge d log C3. That was our differential form for the positive Grassmannian. So omega of g plus 1,3 was just this. And then what we can do, we can just take this equation here and just find out what C2 is. So if you solve for C2, you find that this is just x2 over x1. And we can find can solve for C3, that's just x3 minus x1. So that's just inverting this relation here. And then what happens is that you can just calculate that just substituting. So substituting C2 equals to x2 over x1 and C3 equals to x3 over x1. What you can find the following differential form: x2 over x2 x3 over x1, and remembering that x3 is related to x1 and x2, so this is the same as d log x2 over x1 wedge d log 1 minus x1 minus x2 over x1. You can notice immediately that this is a canonical differential form of this triangle here. So this is just the omega of delta 1,3. Okay, so if I have a map, in that case, is a map going from G plus 1,3 into delta 1,3. If I have a differential form here, so omega G plus 1,3, I can derive a differential form of the image. And this procedure is called, so it's usually, there's an operation on differential forms, and then this operation is called a push forward. It's a push forward of differential forms. So in our case, this push forward is very simple. It's just a substitution. So we had C2 and C3 in terms of the X1, X2, X3, and we just substituted and got the differential form of the image. Okay, so this can be done also for higher hypersimplices. And this is one of your tasks which you have for the second exercise in the problem set for today. And it's quite tedious, but I think a rewarding task, so a rewarding thing to do. So I encourage you to do that. I'll publish these questions later on. Okay, so this is just to say, so I just wanted to introduce this hypersimplex just to say that if you have an object like the hypersimplex, which is the image of a positive Grassmannian through some map, which is this algebraic moment map mu, then you can find the canonical differential forms of the image just knowing the canonical differential form on the positive Grassmannian. And since we know canonical differential forms on the positive Grassmannian for all positive Grassmannians, that's quite easy thing to do. And it allows you to find a larger class of canonical forms using this idea of push forwards and then later on also triangulations. Okay. So I think that my time for today is slowly finishing. There were some questions, so I hope that that's not too late now. But what we'll do next time, so this is one example where you can construct new positive geometry using positive Grassmannian. And tomorrow, what we'll do, we'll use positive Grassmannian as some different function in order to define what the amplitude is. And then we will, so the amplitude will be an image, so it will be the image of the positive Grassmannian through some other map. And then I will tell you how this, so we will find what the canonical form on this image is using this push forward idea. And then I will tell you how to extract amplitudes in planar n equals to 4 at 3 level using this idea. Okay, so that's the idea for tomorrow.
Great. So yeah, maybe we have time for a couple of quick questions if people want to ask.
So I had a question from earlier that wasn't completely answered. So I was wondering so these coordinate-free differential forms, how do you get them? And maybe a simpler question would be, since the positive Grassmannian is the generalization, of projective space, like, is it possible to see how to get this canonical form from the canonical form from projective space?
So I mean, there's a similar formula for projective spaces. So what the projective space equivalent would be. So if you take P n minus 1, this P n minus 1 can be parameterized by x1, x2 up to xn modulo GL1, right? Because modulo rescalings. And then sorry, let me use C's just to make it more clear, the relation to the other one. So C1, Cn. And then I can write this as DNC, so the product of all possible C's, modulo GL1 divided by C1, C2 up to Cn. Okay, so on the projective space, on the positive part of the projective space, that would be the canonical form.
Could you say like a word or two about how you get these forms in the first place? or I guess maybe it's, yeah, okay. Maybe it's,
I think that yeah, so I don't know first principle derivation of it. This is something which mathematicians knew for a very long time. And I'm not sure how they arrived to this formula, but there are some things which you can say about this form. So the form has to be invariant under GLK. So for example, in this case, the only invariant objects for G2,4, I'm sorry, where I am. Here, okay. So the only invariant thing, the only invariant GL2 invariant objects on G plus 2,4 are the maximal minors, right? So it has to only depend on maximal minors. Okay, and then moreover, it has to have proper scaling. So this is a scaling invariant. So if I rescale all the C's by that's correct, right? So if I rescale all the C's by some common factor, then this should be invariant. And then another thing which we know about this, so this should be a canonical form on the positive part of the Grassmannian. So the positive part of the Grassmannian, you can check what are the boundaries of the positive part, and there are just 4 of them. So when it is quite obvious in this parameterization where you have alpha, beta, gamma, and delta. So the positive part of the Grassmannian has boundaries where the minor 1, 2, or 2, 3, or 3, 4, or for 1 is equal to 0. So that indicates that this kind of singularity should be there in the denominator. So this almost immediately fixes this to a unique form.
okay, thanks.
Is there any other very quick question? Otherwise, we can. If not, we can thank Tomek, and yeah, we will see. Okay, this afternoon there will be no tutorial session, but there will be lecture by the second lecture by Sabrina, and then the presentation of the SAGEX movie. So see you later.